The last case, okay, is called deferred annuities. Defer means it's delayed, means the annuity does not occur at the end of the first period. Okay, so just to think about the regular annuity, we draw it like this. And the rule is the annuity occurs at the beginning of the first, at the end of the first period. Okay, and we call it ordinary annuities. That's the annuity problem we have seen. But now we want to learn a new type of annuity problem, which is called deferred annuity, which means the first annuity itself, it started at the end of not the first period, but some later time. Because it's some later time, so we say it's J plus 1 period. Okay, we don't know what is J. It could be the 6th period, it could be the 60th period. It's just some later time. But we know it's not at the end of the first period. So for this type of annuity, we call it deferred annuity. Okay, and then for this type of annuity, we have a new equation to calculate the present value. Okay, so if you have some delayed annuity, it's not happen at the end of the first period, but at some later time. How do you convert that back to the present time? I mean the time 0. Okay, so this is the equation you want to use. And look at this equation. It's A times P slash A I% N minus J. Okay, so now you need to know what is N and also what is J. So what is J? J is here. J is just the you need to know like when the annuity, the first annuity occur, and that time minus 1 is gonna be the J. Okay, so don't worry if you don't understand that, and then we can learn that from this example. Okay. Okay, but after that first factor, you also need to find out a second factor, which is P slash F, I% and J. So very important, you need to find out the J. Okay, let's read this example and you will know what do I mean by find out the J. So suppose that a father, on the day his son is born, that's the present time, that's the 0, okay, that's time 0. So the father at the beginning wishes to determine what lump amount would have to be paid into an account bearing interest of 12% per year, so that it can provide withdrawals of 2,000 on each of the son's 18th, 19th, 20th, and 21st birthdays. How sweet it is. So the father wants to save amount of money when his son was born. And then what he wants is after 17 years, at the end of the 17 years, his son can withdraw some 2,000 from that account on his 18th birthday. And then he could do the same thing on his 19th birthday and 20th birthday and 21st birthday. So this is a deferred annuity problem, because that annuity, the 2,000, the same amount every year, that does not happen at the end of the first year. Okay, it happened at a later time, which is the 16th birthday. So now let's just draw this diagram. Okay, so you can look at it from the viewpoint of the father. So from the father's point of view, and then let's draw this timeline. So 0, that's when the son was born. 1, that's his first birthday. 2, second birthday. 3, third birthday. Nothing happened because the father wants him to withdraw the money from at the 18th birthday and 19th birthday, 20th birthday until the 21st birthday. Okay? And then so if you look at it from the father's point of view, which is the same as the bank's point of view, of course. So the father will spend some amount out of his pocket. Okay, so he wants to know how much he has to spend at the beginning. So that's a dashed arrow going downward. Okay, that's the P. You don't know. So it's a question mark. And starting from the 18th birthday, his son will receive 2,000, okay, every year after the 18th birthday. So that's a receive. The money you receive is gonna be the money going upward. The arrow is going upward. Okay, so it's gonna be small arrows like this, but the same length for the 4 years. And then that's the A, and A is 2,000. Okay, and you know that the I is 12%. So now you need to know, okay, what is the P? And to know the P, you want to use this equation, okay? But the first thing is you need to find out the J, all right? So what is the J? So compare this where the first cash flow, first annuity happened. That's what we call J plus 1, the time J plus 1. And then compare that to this. Look at that. Okay, so this is the thing you're looking at. That's the first annuity. And the number of periods is 18. Okay, and 18 is what? Is in this formula, and I mean in this general diagram, it's gonna be J plus 1. Okay, so if 18 equals to J plus 1, what is J? J is gonna be 17, right? So J is 17 in this problem. That's what you know. Okay, so now you can use this formula. So P is A times P slash A, okay, I% N minus J. N is what? N is 21. J is what? J is 17. Times another factor, which is P slash F, I% and J, which is 17. Okay, now you understand why do I say J is very important. And you got to find a way to find out J. And the way you find it out is you to compare this, the first annuity, when it happened, and use that year minus 1. That's your J. Okay? So let's continue. A is 2,000. And the first factor is P slash A. I is what? 12%. 21 minus 17 is what? Is 4. Another factor, P slash F. I is 12%. N is 17. Okay? Now you just need to check the table. Okay? So the first factor is P slash A. So to find P given A, that's the column you're looking at. And number of periods is 4. So this is the row. Okay? And so this is the first factor you're going to use. So you just write it down here. It's 3.8 0.0373. Second factor, P slash F. P slash F. So this is the column you're looking at. And N is 17. Okay, so 17 is here. So that's the second factor's row you're looking at. So this is the factor, okay, the value of the second factor. So it is 0.1456. So calculate that. Then you will get 884.46. Sounds a good deal. Because your father only needs to put like lower than 900 into the bank, and then after 18 years you can get 2,000. Wow, every year for 4 times. Sounds a good deal for me. Okay, so plan your saving as early as possible, right? But this problem is what we call deferred annuity. So the tricky point is you need to find out the J. Okay, and once you find out the right J, you don't have any problem calculating it. Just use this equation.